Video, we're going to do a quick review of chemical reactions. A chemical reaction is where you have reactants that interact together, chemicals that interact together to produce new chemicals. So I'll give you an example of something that's not a chemical reaction first. So for example, if I had H2O written like this with little s over here, that means you have solid H2O. And then we show you an arrow like this, and we still write H2O, so it's still H2O here. But there's a little L next to it. What that's going to mean is that our solid H2O became liquid H2O, so it melted. This would be an example of a physical change because we still have H2O. It's still the same chemical identity at the end. So this was not a chemical reaction. In a chemical reaction, you have a different chemical identity, a new chemical identity that has formed. So if you look at this example here, we have zinc plus hydrochloric acid. Oops. Zinc plus hydrochloric acid. So they're reacting there to produce something new. They're producing hydrogen and zinc chloride. So you started off with zinc and hydrochloric acid, and now you have these new molecules and compounds that are formed after that reaction. That would be a chemical reaction. A chemical reaction can be represented by something called a word equation, or you could also represent it by something called a chemical equation. So in a word equation, you represent what's going on using the words of the chemicals involved. So you'll notice there's an arrow here. That arrow means to form. On the left side of the arrow, so right here, we put our reactants, the ingredients, the things you start off with. So zinc reacting with hydrochloric acid. The plus means reacts with, so zinc reacts with hydrochloric acid. The arrow means to produce or yields, so to produce. And on the right side, we have our products, what's made in the end. So we have hydrogen plus zinc chloride. On the right side, the product side, the plus means end. So let's read that together. Zinc reacts with hydrochloric acid to produce hydrogen and zinc chloride. So you need to be able to identify your reactants and your products. This is a word equation. Here's another example of a word equation. Again, we have our reactants on the left side, our products on the right side. Notice that you can actually write energy in an equation. If energy is released, is given off by the reaction, you can write the energy on the product side, and we would say that's an exothermic reaction. Exo meaning to exit, so the energy exits the system, is released. If, on the other hand, the energy was used or absorbed during the reaction, you would write it on the reactants side, and you would call that reaction endothermic in terms of energy. It's taking in energy, endothermic. So one thing I do want to make clear is that when you're writing word equations, you don't want to show the states of your reactants and products. You don't want to say, for example, if you knew magnesium was solid, you don't want to write solid magnesium. You just want to write down what the reactant is and what the products are without any states given. You can include states in a different type of equation, and that equation is called a chemical equation. So if we go down below over here, you'll notice that there are some equations. The ones that we saw up here represented using their formulas and their symbols. So a chemical equation is a bit easier to write. There's less to write because you're using the symbols and the formulas for the reactants and products. So for example, we have zinc written as its symbol over here, hydrochloric acid written as its formula over here, HCl, and then hydrogen gas written as its formula over here. Notice that little 2 there. There's a 2 there because that's a P.S. Bofinch or P.S. Hofbrinkel element. So those elements, you need to remember them because when you write them down in chemical equations, you're going to have to put their subscripts as you learn them in class with the 2s or the 4s for phosphorus and 8 for sulfur. And you have to put their state as well to represent them in a chemical equation. And you'll notice here we have zinc chloride and it's aqueous, dissolved. Aqueous means dissolved in water. So in a chemical equation, you can represent reactants with their symbols and formulas, and you can also show their states as subscripts using S for solid, L for liquid, G for gases, and then AQ for dissolved in water. Here you can see magnesium with its symbol, oxygen O2 because it's Hofbrinkel, and then it's they're reacting to produce MgO. It's solid and energy was released. Energy is just written as a word, it doesn't really matter. And you'll notice that I told you that the O has to have a 2 at the bottom of it, and that's because it's a Hofbrinkel element. You'll notice over here, however, that it doesn't have a 2. So your Hofbrinkel elements will only have those 2s and 4s and 8s when they're alone. That means not in the compound. When they are in a compound, you need to make sure you're using your crisscross rules and your formula writing rules to figure out what their subscripts are going to be. So Hofbrinkel rules really only apply when they're reacting individually and not in a compound form. So for MgO, you're not going to have MgO2 because you're doing the crisscross between Mg plus 2 and O minus 2 since it is an ionic compound. So you should make sure that you review how to write formulas for the different types of compounds that we saw, and you review those PS, Bofinch, or Hofbrinkel elements because they will come back into play when you're writing down these chemical equations and these word equations. So we'll do a sample problem together. We'll do this one at the bottom over here first. So we have a reaction when solid sodium metal reacts with chlorine gas, solid sodium chloride is formed and energy is released. So your first step is to identify your reactants. So you can see the way it's written here. Solid sodium metal reacts with chlorine gas. Those are your reactants. Highlight them in red here. And we see that solid sodium chloride is formed and energy is released. So those are your products. We'll put them in green. So for your word equation, don't put any states. Just write down the reactants, their names. So sodium plus chlorine. Don't put the state. They're reacting to produce, so put your arrow. Sodium chloride. Don't put the state of the salt. Don't put the state of the sodium chloride either. So sodium chloride. And we see that energy is released. So plus energy. Because energy is released, you put it on the product side. Write your chemical equation. Now you can include states. You're going to use your symbols. So we're going to write down our sodium symbol first, Na, and it's solid. I'll go back to make them subscripts in just a bit. We're going to have our chlorine as well as a reactant, so Cl. Don't forget that's a Hofbrinkel element, and we know when it's Hofbrinkel, it's in its gas form. And then we have it's producing sodium chloride. So to figure out the formula for sodium chloride, you need to use your crisscross method since it's an ionic compound, Na plus, Cl minus. Do your crisscross or your charge balancing, and you get NaCl in its solid form based on the description, plus energy. You can make sure these are subscripts. Now, you won't always be given states for your reactants and products. So if you aren't given states, at least right now, you might not be expected to write them, but later on you will be, as you'll be given some hints and tips on how to figure out what their states should be. For your Hofbrinkels, though, you should know what their states are based on the package that we did for naming compounds and writing formulas for compounds. If you look at your polyatomic elements, you'll find those states there. So that was an example of writing a word equation and a chemical equation. You may have also seen chemical equations sometimes called a skeleton equation when it's not balanced, meaning when the number of atoms of each type is not the same on both sides. So for example, on this side of the equation, the left side, I have one sodium, that's fine. But you'll notice here I have Cl2, so 2 chlorines, but only 1 chlorine on that side, so it's not a balanced equation. So when it's not balanced, some textbooks and resources will call it a skeleton chemical equation, and some people just refer to it as a chemical equation. In the next video, we're going to see how to balance equations from their skeleton equations. So again, word equation, just use the words, don't use the states. Make sure that you then translate it into a chemical equation. You're using the symbols. If you have a Hofbrinkel element alone, not in a compound, you're going to use the subscript and the subscript that was told to you, so either the 2, the 4, the 8. And when you have compounds, you have to use the rules to turn them into their formulas, and they all apply for ionics, moleculars, hydrates, polyatomic elements, so on and so forth. And if energy is released, write it on the reactant side. If it's absorbed, write it on the product side. You should go back and try this example here. The answers are in the notes that were given to you.